Yo, welcome back, guys. Episode 72. Another day, more problems. That didn't really go together, but it's okay. Yeah, we're gonna check out our Pokemon sound of the day. We got a little morning session right here before work. Run through some problems. So let's take a look at Pokemon 72. What we got today. In the original Pokemon is red, blue, and yellow. Pokemon 72 is tentacle or water. Okay. Tentacool. Tentacool. Sound. Ba-da-dip. Ba-da-doop. Ba-da-doop. Ba-da-dip. Ba-da-doop. That's kind of the sound. Ba-da-dip. There's our Pokemon sound of the day. Let's take a look at Leetcode's problem of the day, shall we? See what we got today. Minimum operations to make binary array elements equal to 1. Is this another bitwise bit manipulation? And a sliding window. You're given a binary array nums. You can do the following operations on the array any number of times, possibly 0. Choose any 3 consecutive elements from an array and flip all of them. Flipping an element means changing its value from 0 to 1 and from 1 to 0. Return the minimum number of operations required to make all elements and nums equal to 1. If it is impossible, return -1. Okay. So I can see why it kind of is a sliding window problem. So we're given any 3 consecutive, right? 3. We flip these. It's 1, 0, 0, 0. Then we go here. It's 1, 1, 0. And then we go here. Okay. Let's try and simulate this in a paint, right? I'm curious to see if this is I can't see this being the algorithm. I don't know. Maybe it is. 1, 1, 1, 0, 0. Right, so we start with these 3, right? We flip these. It becomes 1, 0, 0, 1, 0, 0. And then we're here, right? Sorry. Then we're here. This is our sliding window. We flip these, so we go 1, 1, 1, 0, 0, 0. And then we're here, taking these 3 numbers. Then we do our flip, 0, 1, 1, 0. Right, but then we're here, we flip again, 1, 1, 0, 0, 0, 1. And then we're here. Oh. So no, that's not the algorithm. Choosing opportunity 0 and 1. Wow, these are great fucking hints, man. Like, I overestimated so much this question. Oh my god. Thought writing guys don't ever think it would be accepted. trying to think here. So, trying to think. Is it a different sort of sliding window problem? Maybe we have to like always reset our left and right pointers or something. I don't know. Like 3191 minimum operations to make binary array elements equal to 1. Give me some hints. No code. 0 and 1s. Yeah. Got an email, man. Okay. Place a Windows centered at 1 to cover as many zeros as possible. To be honest, I'm not sure. Let's take a look at this guy's solution.
Welcome back, and let's write some more Leetcode today. So today let's solve the problem minimum operations to make binary array elements equal to 1. I guess that's the first variation of this problem. But anyways, idea is pretty simple. We're given an array that consists of zeros and ones, so it's a binary array. The first example looks like this. And we want to transform this into an array that is all ones. So that would look like this. We're only allowed to do that by changing 3 contiguous elements at a time. So we could change these 3, or we could change these 3, or we could change these 3, or we could change these 3. You're probably thinking, I'm going kind of slow so far, and I guess, to be honest, I'm kind of deliberately slowing myself down, because as soon as I saw this problem and as soon as I finished reading the description, it became pretty clear to me how to solve this problem. Because first of all, that 3 consecutive element thing, I mean, it just looks like a sliding window. So maybe they're trying to trip us up, but I went for it anyway. I went for the bait that they gave us. It seems like a sliding window problem. Let me just see if maybe there's a sliding window solution. Well, it seems, though, that maybe it would involve backtracking, right? Maybe some of you thought that this could be a backtracking problem. I thought that's definitely possible. If I can't find a sliding window solution, that's going to be the next thing I probably consider. But then I asked myself, because with backtracking, like if I flip this window, that might not be the correct decision. Maybe we're not supposed to flip this window. Maybe we're supposed to flip the next window like this. How do you know? It seems like we have no way of knowing, right? Well, then the idea came to my mind. There's probably a trick behind it that made me think along the lines of greedy, and then I saw it immediately. Do you see it? Because I see it.
No, I don't see it.
Take a look at this. If I want to flip this bit, well, I probably wouldn't want to flip it. It's already a 1. But if I did want to flip it, well, I could do this window, or I could do this window over here. That also includes this guy. Or I could do this window over there. All 3 windows include this middle element. If I wanted to flip it, I could choose 3 different windows. My God, this seems pretty complicated, right? No, I promise you, it's not complicated, because greedy is going to help us. Because consider this. What about the guy over here? How many different windows does he get to choose from? Only a single one. So now, you tell me, is there actually 3 choices? Or maybe there's actually just 2 choices? Or actually, maybe there's just 1 choice, and that's what I'm here to tell you. There's really only 1 choice. And the idea is this. If this is a 0, there's only one way to flip it into a 1. I only have 1 choice. I have to do this window. I have no other choice. Now, of course, you might be thinking, well, if I end up turning this into a 1, that kind of sucks, because then I have to turn these, or these 2, into zeros. And you're right, it does suck, but it was necessary. And it's okay, because now we can flip the next window as well. Because we're going to assume that everything before our current pointer is already 1. Don't touch any of that, because it's already good. And we had to flip that bit. So now everything before this line is good. I mean, we could, if we wanted to, we could go back for some reason and do another flip. But I mean, why would we do that? Why would we want to unset some of these bits? Why would we want to basically undo the work that we already did? We wouldn't. So we don't touch anything before that line. And now we have a sub-problem. This is the rest of the array. How many flips is it going to take to make this thing 0? Well, once again, just go greedy. Just look at the current element only. If this is 0, well, nothing else matters. It has to be flipped. We have to do this specific window. It has to be, because we're not going to touch anything before, and we don't want to do this window. That doesn't include this guy, so we have to include this window. We flip it. We don't care about what happens to these 2. Well, we do care, but it's not going to change the result. Then we might have to flip those, we might not. So now we look at this window, we flip it as well. We end up getting a 1 here and a 1 here and then a 0 here. And then our eye pointer will be over here now. We'll look at the next window. Well, specifically only this element. It's 1, so we're good. Go to the next iteration. Now our eye pointer is going to be...
That's so smart, bro. I would have never... Oh my gosh. That's so smart, dude. Okay. Let's put a comment here, greedy, right? So we loop through for right, and range, length, nums. We need a res array that keeps track of our pointers. We need a left pointer, right? Let's make it like a K pointer to just the size of our window, right? Okay, so if if K to this cat, bro, it's insane. Right minus left plus 1 is equal to K. Size of window, right? Okay, and equal to K, then we flip each element. How do we flip each element? Plus 1 is equal to K, size of window. How do we flip? Like we need a different pointer to flip, no, right? Unless we move our left pointer forward. Right, I think that's what we have to do. Well, we have to do, well, if so if we go then we need while left does not equal right, if num's left is equal to 0, then num's left is equal to 1, else num's left is equal to 0. Let's see what it returns. Oh shit, we didn't. Okay. That's plus equal to 1. Are we getting a... Oh shit, we need to increase our left as well. After each iteration. So that's plus equal to 1. Okay. What we're missing here is that we're checking the leftmost value, so and left is equal to 0, right? Because it has to be. We don't fuck with any of them that are 1. If num's left is equal to 1, left plus equal to 1. No. Clicking in this bitch on lunch, she go. Do 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 do. Okay.
So what I'm going to do is have my result. That's going to count the number of operations. That's what we're going to return. And I don't know why my code syntax highlighting isn't working. Okay, just needed to refresh. But then we're going to go through every index in the input. And I'm going to do it like this. Take the length of the array and subtract 2 from it. And then I'm going to check if the current number at index I is equal to 0, well, then we perform a flip, and we're going to have to increment our result. Off the top of my head, I feel like a helper function might be useful for the flip, so I'm going to do something like this, passing in the nums array, which we probably don't have to do, but definitely should pass in the index that we want to flip, and then I can just update nums at index I and flip it with a ternary operator, so 0, if the number is non-zero, otherwise it will be set to 1. And so then here I can just call flip on nums, passing in I, passing in I plus 1, and passing in I plus 2. And then after all of that, well, now I just kind of realized that I forgot to mention how we know if it's invalid. So since we're doing all the ones up front, we know that it's invalid because we will stop 2 elements before the end. So we want to look at the last 2 elements. It's possible that they're both 0 because we didn't flip them. We didn't even look at them. If they're both 0, then obviously we return -1. If one of them is 0, but the other one isn't 0, still we return -1 because we're never going to be able to flip this guy alone or 2 of these alone. We have to do 3 at a time. But if they're both 1, then we are good. So that's the idea here. So we'll say if not nums at -1 in Python, that gives us the last element, or not nums at -2 in Python, that gives us the second to last element. In this case, we return -1, and we're guaranteed that at least 2 elements are going to exist in the nums array, so we don't need to check the length or anything like that. And this is the whole code. Of course, I don't even know how I did that, but I made it a plural for some reason. Flips should be flip. And you can see here that it works, and I promise you.
Okay, here. If nums I is equal to 0, found a 0, flip the next k elements. If I plus k is greater than n, not enough space to flip, return -1. Then we flip the k size window. We loop from j from the position I to I plus k. Nums j is equal to 1. Another interesting solution. Alright, I'm going to try not to look at it. If nums I is equal to 0, we need to perform the flips. Oh, my back, dude. Oh my gosh, bruh. And the length of nums out of bounds. We can turn -1, right? Otherwise, if we do the flipping, right? For j in range I to I plus k, window size, then we def flip. We can put in the kind of want to do a separate function just to, you do something different. Chain range I to I plus k. Sorry, I feel like this is J, my bad. Flip nums I. Right, is that how he does it? If nums J. Equal to 1, then equal to 0, else nums J is equal to 1. We flip. Then we increase our res. Then we return our res. Yay. Nice. Nice, 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 nice. Cool. Okay, let's jump into some more problems. Let's check out, of course, we have to do our classic binary tree. Our classic binary search problem of the day. DFS, PFS, whatever that may be. Flatten binary tree to linked list. I'm Number of good leaf node pairs. You're given a root of a binary tree and it is your distance. A pair of two different leaf nodes of a binary tree is said to be good if the length of the shortest path between them is less or equal to distance. Wait, what? The root of a binary tree, integer distance. Okay, a pair of two different leaf nodes. I'm a little confused right now. I don't really understand what the question is asking me. Number of good leaf node. Understand the question. A good pair of leaf node. Oh, leaf node pairs. Okay. A good pair of leaf nodes is defined as both nodes are leaves, nodes with no children. The shortest path between them is less than the distance. Task is to count the number of good leaf node pairs. Given the distance 3. Leaf nodes 4, 5, and 6. Possible pairs 4, 5, 4, 6, 5, 6. 4 and 5. 4, 2, 1, 3, 5. Okay. Distance is 4. 1, 2, 3, 4. Okay. 5 and 6. 2 valid. Okay. Okay, I understand the question now. But how would you solve this problem? Well, this would be a recursive problem, but it's got a high acceptance rate. Where's the acceptance rate? I don't hear it. 71. You can get a Leetcode hoodie from Upvotes, bro. What? Leetcode hoodie. Bro, no way. There's a store on here, bro. Oh, I got 569 points. Time travel ticket. Travel back in time. Finish one missing challenge. Notebook with big O chart. Exclusive Leetcode kit. No way, bro. Daily check-in last month. Weekly premium challenges 35. Contribute a question. Contribute a test case. Oh, this is cool, then. Alright. It's a tough one. Instead of comparing every leaf pair over and squared, use DFS with post order. DFS, passing out root. Alright. Call our DFS function, passing our root, right? We check, well, if not node, then we just return, right? Then we want to do our left subtree first. So if we go left, the left is equal to DFS or the left. I'm actually not sure how to solve this. Oh, Jesus. Dude, I don't really know how to do this. Man, this is a tough problem, dude. Okay. So we have DFS. How's we gonna DFS no dot left? It's an interesting solution. For not root the left, so if this is a child, we have a descendants array. Right now, non-local, we have our left is equal to dfs root dot left. If root dot left, else that. Empty array. Empty list. For I in left, we're going to take a look at the solution, analyze the solution. Man, it's cold in here, bro. It's so cold. Okay, we're gonna attempt this code. Okay, if not node, we just want to return none, right? Okay, we want a total variable, right? Okay, if not node dot left and not node dot right, we just want to return 1, right? That's our base case, the leaf node. Okay. Create a descendants thing, create a non-local variable so we can edit it, right? Non-local total. Okay. Then we do, well, left is equal to DFS root dot left. Right is equal to DFS root dot right. If root dot left, else this. If root dot right, else. So if for I in left, oh my gosh, whoops, for I in left, if I is less than or equal to distance, equal to distance, then what, we just continue, right? Greater in left, no need to check right subtree. Okay. Else if, oh no, we do another for J in right. If plus j plus center equal to distance. Then we found a pair, right? So total plus equal to 1. Then we want to return I plus 1 for I in left plus right. My back, man. Oh. Maximum recursion depth exceeded. I'm gonna turn this air conditioning off, man. Oh my god. Ah, it's cold, dude. Okay. The left else. DFS root or left. If root or left else. Oh man. Oh jeez. Okay. Because of the root here. This needs to be node. Oh, man. Sneezing, bro. Okay. Initial call DFS 1, we got node 1, left child. As of course, DFS 2, DFS 2, DFS 3. Right, recursive call DFS 2, 2, we got left child 4, right child 5, yeah. It's called DFS 4, we're going all the way down here. We return our base case 1 because it's a leaf node. We return DFS 2 with left is equal to 1. Right, then we go here, DFS 5, return 1 because it's a leaf node, yeah. Now we're at DFS 2, right? So we're in this part here. left 1 and right 1 from node 5 count pairs for I is equal to 1 from left. I plus j is equal to 1 plus 1 is equal to 2, which is less than or equal to 3 valid pair, increment total by 1. Okay. Return I plus 1 for I in left plus right. Oh, I plus 1 for I in left plus right. DFS 3, right? Keep going. Yeah, we return 1 and 1, and then we come back to DFS 3 here, right? We do the same thing. Total by 1. Return 2 to DFS 1. Okay. 1 level up. Back to DFS 1. Now we have left 2, 2 from node 2 and right 2, 2 from node 3 count pairs. For I is equal to 2 from left, check against j is equal to 2 from right. I plus j is equal to 2 plus 2 is 4, which is greater than 3, so no valid pair. For I is equal to 2 from left, check against j is equal to 2 from, which is greater than 3, so no valid pair. Okay. Okay, I understand the solution now. It's interesting solution. It was definitely, I would have never got that problem ever. It's definitely like just a learning curve, you know what I mean? I kind of want to look at the post order traversal, how we did it again. We use a stack here to simulate it, if not root. Stack is equal to root. While stack node is equal to stacked up hop. Did this a little while ago, yeah, about a month ago. Stack, we pop our node, which is our root. We append our val. Okay. Could you do it iteratively? Let's do a recursive solution of this. We'll post order left, right, root. So DFS root. Turn root. Then we do if node dot left. That's not alright. But we want to return a list, so... No, reservoir out here, right? Return. I just realized I'm not even calling the function. DFS root. Okay. Would this work? Same thing, I think it works. Okay. Okay. Let's do... might as well go to Leetcode 75 for a bit. Let's take a look at some stuff. Let's take a look at this hash map set problem we haven't done before. Ooh, a grid. Ooh. Actually, n times n integer grid. Return the number of pairs such that row I equal in the same order. This should be easy. I don't really understand the problem, to be honest. 2, 3, 5, 2 equal row and column pairs. Can you help me? Problem better. Looking for IJ where row I is equal to column J. Sometimes a row is the same as a column. Oh, row 2, column 1. Ah, okay. I know. 277, 277. Right, okay. 3, 1, 2, 2, 3, 1, 2, 2. 2, 4. Oh, Gucci B, I'm trying to fuck up with it. Show me some more. Okay, give it a 0 to x and times n integer matrix grid, return the number of. It's considered equal if they contain the same elements in the same order, an equal array. Okay. I'm not good with grid problems yet, but. Okay. For I in range length nums. For J in range length nums. Right? Double for loop here. Let's print I. Right? I'm just curious. We print I. Should print the. Bruh. Arms is not defined. Ugh, grid, dude. Print J. Okay. Okay, let's print nums I. Then we print nums J. Oh my god, dude. Grid. 3, 2, 1, 3, 2, 1. 3, 2, 1, 3, 2, 1. 176. 277. Okay, wait, I'm confused. Okay, so we got 3, 2, 1 here. Then we got I kind of know how to solve this problem, you know? Like, I mean, we're asking for the rows and columns, right? That equal, right? An equal row and column pair, right? So like 3, 1, 2. In this case, it's 277, 277, right? They're equal, right? And I know that we got pretty much got to loop through the rows, save the rows in a hash map, but because we can't put lists inside of a hash map, we save it as a tuple. So we convert this list to a tuple, or this row, and then if we see the column, then we know we found a match and we just increment by 1. But I don't know, I'm not very familiar with, you know, double lists and like, you know, working like this. I'm just not, I haven't really learned, you know, exactly how to think about it this way using these problems. So like, I don't know, maybe we can watch an Leetcode video. Equal row. I'm sure he has one of this. Just because I want to get better. He doesn't. No way, dude. What do you mean this is a matrix simulation? Okay, let's just look. This goes
Is your job boring and tedious? Or maybe you love your job, but you love gaming even more.
Hello and welcome. Today we're doing another question from Leetcode 75, a great playlist if you are interview prepping, and I have the entire playlist linked down below with all the video explanations we've been doing if you do want to check it out. So what is this question? It's equal row and column pair. Given a zero indexed n by n integer matrix grid, return the number of pairs such that row and column are equal. A row and column pair is considered equal if they contain the same elements in the same order, i.e. if they are an equal array. So example 1, we have 3, 2, 1 as a row, 176 as a row, and 277 as a row. And our columns are 3, 1, 2, 277, and 167. So we want to find the pairs of rows and columns that are equal. And what are our equal pairs? Well, we don't have any 3, 2, 1s as columns. We don't have any 176 as a column. We have a 167, but it's out of order, so that's not going to work. And 277, do we have any columns of that? We do. We have one column of 277, and we also have a row of 277. So that's one pair we can make, and that is our output. Example 2, we have the following grid. I'm going to write this out so it's easier to read. We have 3, 1, 2, 2 as a row, and we have 1, 4, 4, 5. We have a 2, 4, 2, 2. And we have another 2, 4, 2, 2. So instead of writing it again, I'm just going to keep count of all the times I've seen all these rows. So I've seen 3, 1, 2, 2 once, I've seen 1, 4, 4, 5 once, and I've seen 2, 4, 2, 2 twice. Now, as I go through the columns, all I'm going to do is check if that column exists in this dictionary of counts that we have going on over here and see how many pairs I can make. So going through the columns, right? 3, 1, 2, 2. Does this exist in our dictionary? It does. We have 3, 1, 2, 2, and we have one of that. So we can make one pair. If I were to keep track of the pairs, I would have one pair so far. My next column is 1, 4, 4, 4. It's not in here, so no pairs are made. Then I have 2, 4, 2, 2. I do have 2, 4, 2, 2, and I have two of those. So we can actually make two pairs, And I'm going to add 2 more to our total pairs. So now we have a total of 3. Then we come across 2, 5, 2, 2. We don't have that in here, so no other pair can be formed. And we've made a total of 3 pairs, just like we were expecting. And this is actually how we want to solve this as well. We just want to take a row and a column as a whole. There's no point in breaking up the individual cells. We only want to check if an entire row equals an entire column. So we can keep them together as an entire entity. Keep track of all the rows we've seen, add it to a dictionary, keep counts of that. Then as we go through all of our columns, see if that entire column exists as a key in our dictionary to count up the number of pairs that we have. So let's go ahead and code this up and then do a complete walkthrough to really see how this plays out. To code this up, what do we want to do? We first want to go through every single row that we have and keep count of it in a dictionary. So in order to do this, I'm going to import from collections a default dictionary. So from collections, import default dict. And all a default dictionary is a regular dictionary with default values already present. So we don't need to check if a key is there. If not, define it first and then increment its counts. We can just directly increment its counts. They're already valued to be 0. So the first thing I'm going to do is define my default dictionary. It's going to be rows. I'm going to call this default dict of int. And now I'm going to loop through all the rows in my grid. So for row in grid. Now I can't take my entire row, the list form of it, and add it as a key to my dictionary. This because a row is not immutable, right? If we have a list, we can just change its values on any given index that we want, but that's not going to work as a key for a dictionary because dictionaries are hashed based on their key. They don't want to be mutable, which is why we can only use strings or tuples as keys for dictionaries, which is why we're going to take our list and just convert it to a tuple. So rows of a tuple of row. So rows is my dictionary, and as a key, I'm going to assign it the tuple version of my list row. I'm just going to add a count for that. I'm going to increment this by 1. Once I loop through this, I have all my counts done for my rows. Now I just want to figure out my columns. So for columns, I'm going to
This is where I don't know.
through n. This is an n by n grid. So let's also define what n is over here. It's just going to be the length of the grid. So for column in range n, I want to make an entire column going down like this. So right now I'm looping through from 0 to n, not inclusive. I want to get every single row at the column that I want. So my column is going to equal grid of r column for r in range n. Now in Python, this is something called list comprehension. If you're not familiar with it, it's just a shorthand version of writing our for loops and making lists. Basically, we're looping through from 1 to n for columns, so 0 to n, not inclusive, right? We're looping through this way. But for all of these column values, we also need to get that grid value from every single row. That's what we're doing here. We're looping through from 0 to n for our rows. So we're going row by row, but we're keeping the columns constant. So every time we do this, we get a new column. And now that we have our column, we also want to actually convert this to a tuple. So now I have a column tuple going vertically. I want to check if it's in my dictionary. So if column in rows, I'm going to increment the pairs that I can make by 1. So in order to do that, I'm also going to initialize pairs to be 0 up here. Now, if the column is in rows, I'm going to add to pairs, so pairs plus equals, the value of the counts at that dictionary. So rows of column. For example, if we come across 2422 as a tuple in our column, we're going to see if it exists in our dictionary of rows. It does. Now we're going to add the value of this tuple, so 2, to the number of pairs that we can make. Now once we exit out of here, all we have to do is return us or to dictionary to add to pairs. So pairs, we're going to here, that's it. So let's go ahead and submit this. And it is accepted. Now before leaving, we're going to do a quick walkthrough with an example just to see how our code is going to run line by line and really visualize this all together. For our code walkthrough, we're going to be using example 1. So I have my grid input right over here. It looks like this over here.
Oh my gosh, dude.
And going through this line by line, the first thing we do is initialize our n. So n n is going to be the length of grid, which is 3. Yours is going to be 0. And I'm initializing rows to be a default dictionary. Now, looping through for every single row in our grid, the first one we come across is 3, 2, 1. This is our row. We're converting it to a tuple, adding it as a key to rows, and increasing the count of that key by 1. By default, it is 0 right now. This is a default dictionary, so it goes to 1 for this tuple. So we have 3, 2, 1 with a count of 1. Now we go back in this for loop. The next row we're on is 176, doing the same thing again. We have 176 as a tuple. Increasing that count by 1 puts us at a total of 1. Going back in this row, we have 277. That as a tuple is this, and we have a value of 1. Now we are out of this for loop. There are no more rows for us to iterate over, so we come into this for loop over here. For column in range n. So column starts off with 0. We're looping through from 0 to 3, not inclusive. The first thing we're going to do is define a column. Now this column is going to be a tuple of grid of r column for r in range n. So what we do is basically loop through r in range n. So 0, 1, 2 are our r values. And for every single 0, 1, 2, we're using a column which is 0. So what do we have at 0, 0? What do we have at 1, 0? And what do we have at 2, 0? That's 3, 1, 2. So right now we have a list of 3, 1, and 2. We convert that into a tuple. And this is our column, right? We set our column equal to this tuple. Now, if column in rows, is this in our dictionary? Is 3, 1, 2 there? It's not, so we exit out of this if and go back into our for loop. So now we are at 1 over here, and we do the same thing again. We keep our column constant, it's 1, and we loop through for rows in range 0 to 3. So what do we have at 0, 1, at 1, 1, and 2, 1? That's 2, 7, 7. We make a tuple of that and assign that to be column. Now we want to check if column in rows. That is true, right? 277 is in our dictionary.
I think we understand now. All right. Let's do this. Okay. Length is equal to the length of grid for row in grid. Let's create a my dictionary for row and grid. Okay. If Maya scored dick tuple row minus dick tuple row plus equal to 1. It's in my dictionary. Else minus dick tuple row is equal to 1. Let's print out grid. See if that works properly. Yeah. Key error 321. Nico tickles you. Nice, bro. Oh, I think we're missing. I think we need like a double one like this. That's what we're missing. We're actually referencing the array. We're referencing the index. For what? think it's maybe grid though. Jesus. Okay, so I can't do it all in one line. Okay. Row tuple is equal to tuple row. And we can check, well, if row tuple in my dictionary, then we add my dic row tuple. Row tuple is equal to 1. I think that should work. There we go. Okay, right, so we did our rows. Now we want to do our columns. So we do, well, for col in grid. How did you do it over here for col in range n? Range length. Then we do column is equal to, I don't know how to do such a list comprehension, man. Expression for item in iterable if condition. In R. For R in range length, right? Yeah. Okay, right. So we used to get the column. Column in my dictionary. Then we just want to, we need a res array in my dictionary. Then res plus or equal to minus dic column. Just return res. What did she do here? She did if column in rows. Oh, she did the same thing as me. Okay. A little frustrating, but yeah. It was a good problem. It was a good problem. We'll leave that for another day, I think. Let's do something simple. Let's reverse the linked list. Let's go back to the OG days. We'll reset this code really quickly. We've done this so many times, bro. September, October, November, January, February. Oh, we did this recently. About a month ago. Okay. We're going to finish on this problem, and then we'll call it a day. I know we need our cur is equal to head. And we need a previous is equal to none, right? While cur does not equal none. We need to set our, how does this go? Next is equal to cur.next, right? We need our next variable here. Right. And we need to reset the link, so our cur.next is equal to previous. And then we want to do our previous is equal to cur. And our cur is equal to next. And we can return, I guess, return our previous. Boom. Boom, 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 boom. Boom, boom. I mean, I should be celebrating that problem so easy, but anyway, okay. I mean, that was too easy. That literally took 1 minute. Let's do... Oh, get rid of this. Reset code. I do remember doing this. It was a little bit ago, but I do remember. You're given asteroids of integers representing asteroids in a row. The indices of the asteroids represent the relative position in space. For each asteroid, the absolute value represents its size, and the sign represents its direction. Positive meaning right, negative meaning left. Each asteroid moves at the same speed. Each asteroid, the absolute value represents its size, and the sign represents its direction. Positive meaning right, negative meaning left. Each asteroid moves at the same speed. Find out the state of the asteroids after all the collisions. If two asteroids meet, the smaller one will explode. Both are the same size, both will explode. Direction will never meet. Okay, so I believe we create a stack, right? And we loop through our values for I in range length asteroids, right? If stack if there's something in the stack and stack -1 stack.append asteroids I. Oh man, I need to go to the bathroom so bad. Both will explode. I have to kind of go to the bathroom, but all right, let's do this. All right, so let's look at our thing. Right, so we have 5. I think we have to visualize this a little better because the intuition isn't coming to me again, even though I've solved the problem. 5, 10, -5, right? Okay, I know that we need to compare the absolute value. So if we somehow have this value, okay, if we somehow add 5 to our stack, right? Let's say that we're at 10, right? And we compare, well, there's 10, the value of the stack, right? We say, well, 10, technically 10 and 5 will never collide because they're both positive. So then we just add 10 to the stack, right? Then if -5 and 10, right? Then since 10 is bigger than -5, right? But they're coming at each other, then -5 will explode. So then we just go to the next value and we don't add it. Let's say it was flipped, right? Let's say this was 15. Okay. Then we check, well, if -15 is 10, then okay, we need a while loop then because we need to keep comparing, right? So then we do -15. It's 10. It would pop 10. Then it would pop 5 as well. So then we'd be at -15 here. Okay, that's what I'm kind of thinking. That kind of makes sense. So I think we need to append stack.append asteroids I, right? Okay, if stack. If there's something inside the stack, then no. Okay, if stack -1, if there's something in the stack, then we compare, well, stack -1, while the absolute value of stack -1 is greater than absolute value of stack -1 is greater than asteroids, the absolute value of wait, we need to check both. We need to check while stack -1 is greater than sorry, no, if okay, no, yeah, if nums I is greater than absolute value of nums I is greater than the absolute value of the top of the stack. Stack -1. And we need to check the direction too. So if it's greater, right? For Valin asteroids. While stack. And the top of our stack is greater than 0. And else stack.append. Oh my gosh, dude. Hi. Hi in asteroids. So while there's something in our stack and the top of our stack is greater than 0 and val is less than 0, we'll stack. And we checking the absolute value here? No. And stack -1 is greater than 0 and val is less than 0, right? So that means going opposite directions, I think, right? Because the top of the stack, if that's greater than 0 and the val is less than 0, so we're checking directions here, then okay, then we check all directions. Sorry. Check each way. So I guess if the absolute value of stack -1 so in this case here we're gonna have 5 in here, right? So we're gonna have 5 here. And then we're gonna compare 10, right? If the absolute value of stack -1 is greater than the absolute value of I, what do we do, right? We just break. We just keep going, right? Else if the absolute value of stack minus 1 is less than the absolute value of I, we stack.pop. So if this value is bigger, then we pop, stack.pop, and we append. We append I. Oh man, I have to go to the bathroom so bad. Hey, that's. Oh. I have to go so bad, dude. I have to go so bad. Oh no. Index is out of range, bro. What? Bro, what am I doing wrong here? Okay. I'm gonna come back to this problem tomorrow because I have to go to the bathroom so bad. Like, oh, dude. Bro. What am I doing? What am I doing? Okay, I'm gonna end the video here. I'm not gonna submit it because I want to do it again tomorrow because I feel like I could have solved this if I just I have to go to the bathroom so bad. So thank you guys for watching. I'll see you guys tomorrow.